if you think Jupiter is massive, think again. Jupiter already feels like a cosmic monster, a planet so large it reshaped our entire solar system. But astronomers have discovered a world that makes even Jupiter look small. Not heavier, not denser, just bigger. A planet so inflated, so extreme, that its very existence challenges what we thought planets could be. And before we get to that impossible giant, we need to start at home and climb the ladder of size, one world at a time. Earth feels enormous from the ground. Oceans stretch beyond the horizon. Mountains scrape the sky. Entire civilizations fit comfortably on its surface. Earth's radius is about 6,400 kilometers, just large enough to hold liquid water, a stable atmosphere, and life itself. But place Earth next to Jupiter, and our planet almost disappears. Jupiter is more than 11 times wider than Earth. You could fit over 1,300 Earths inside its volume and still have room left over. It's a world without a solid surface, made almost entirely of hydrogen and helium. Storms rage there for centuries. The Great Red Spot alone, a single storm, is large enough to swallow multiple Earths whole. In our solar system, Jupiter isn't just big. It defines what giant means. Or at least, we thought it did. For a long time, Jupiter was our upper limit. Every planet we knew followed a familiar pattern. Small, rocky worlds close to their stars, large gas giants farther out. That made sense. Gas giants needed cold environments to form, where light gases wouldn't be blown away by stellar radiation. Jupiter fit that model perfectly. But once astronomers started finding planets beyond our solar system, that neat picture began to fall apart. They found gas giants orbiting scorchingly close to stars, worlds completing full orbits in just days, planets where a year lasted less than a week. And among them, one planet stood out, not because it was the most massive, but because it was the most swollen. Meet HAT-P-67b, located roughly 1,200 light-years away in the constellation Hercules. But the planet orbits a star hotter and brighter than our Sun. By mass, it's unremarkable. In fact, it's lighter than Jupiter. But by size, that's where things get strange. HAT-P-67b has a radius more than twice that of Jupiter, stretching to nearly 150,000 kilometers across. That makes it the largest planet ever discovered by radius. Not the heaviest, not the densest, simply the biggest. And that difference matters, because size without mass leads to something deeply unsettling. When astronomers call HAT-P-67b the biggest planet ever found, they are being very specific. In space, big can mean two different things. It can mean mass, how much material a planet contains, or it can mean size, how far that material extends outward in space. Jupiter still wins when it comes to mass. It remains the heaviest planet we know. But HAT-P-67b wins in radius. Its atmosphere stretches so far from its core that the planet occupies more space than any known world. Planets are not solid objects. They are layered systems, cores, deep atmospheres, upper atmospheres, and escaping gas. And in extreme environments, those outer layers can grow far beyond what intuition expects. That's exactly what's happening here. HAT-P-67b has only about 1/3 of Jupiter's mass, spread across more than twice the volume. That gives its average density so low, it borders on the absurd. It's one of the fluffiest objects observed orbiting a star. In theory, under purely hypothetical conditions, its density is low enough that if an ocean large enough could exist, the planet would float. Of course, such an ocean can't exist. But the comparison reveals the core problem. This planet is too big for how little mass it has. Physics do not like that combination. So how did it happen? The answer lies in where this planet lives. HAT-P-67b orbits its star at a distance of just 0.065 astronomical units, roughly 10 million kilometers. That's nearly 6 times closer than Mercury is to the Sun. Because of that, the planet completes one full orbit in less than 5 Earth days. A year on this planet is shorter than a work week. Its host star is an F-type star, hotter, brighter, and larger than our Sun, emitting intense radiation. And that radiation changes everything. HAT-P-67b belongs to a class of worlds known as hot Jupiters. These are gas giants that orbit extremely close to their stars, absorbing enormous amounts of energy. On HAT-P-67b, temperatures reach around 1900 Kelvin, hot enough to melt many metals. That heat doesn't just warm the planet, it expands it. Gas heats up, hot gas expands, and when gravity is relatively weak, the atmosphere swells outward like a balloon. Astronomers call this atmospheric inflation. The closer a gas giant is to its star, the more its atmosphere puffs up. But HAT-P-67b pushes this effect to the extreme. The intense radiation from its star doesn't stop heating the planet. It ionizes the upper atmosphere, stripping electrons from hydrogen atoms and accelerating gas into space. HAT-P-67b is losing atmosphere at an estimated rate of millions of tons every second. The escaping gas forms a vast envelope around the planet, dominated by hydrogen and helium. In some observations, this extended atmosphere stretches several times the size of Jupiter itself, creating a faint, comet-like cloud trailing this planet as it orbits. This isn't just a big planet. It's a planet in the process of falling apart. Normally, gravity keeps a planet compact. More mass means stronger gravity. Stronger gravity means tighter atmospheres. But HAT-P-67b breaks that balance. Its gravity is relatively weak for its size, and the extreme heat from its star gives gas particles enormous energy. At high altitude temperatures, atmospheric particles move faster and faster. Some reach escape velocity. Once that happens, the planet can no longer hold onto them. This creates a feedback loop. Heat expands the atmosphere. Expansion weakens gravity's grip. Weaker gravity allows more gas to escape. The planet doesn't explode. It slowly bleeds. What makes HAT-P-67b truly fascinating is that we are likely observing it during a brief phase of its life. It probably didn't always look like this. Earlier in history, it may have been smaller, denser, and more stable. But as it migrated inward towards its star, conditions changed. Radiation intensified, atmospheric escape accelerated, inflation took over. For astronomers, this planet is not just an oddity. It's a snapshot, a glimpse of what happens when planetary systems push physics too far. HAT-P-67b will not remain the biggest planet forever. As it continues to lose gas, its radius will shrink. Over time, it may resemble a much smaller hot Jupiter, or even a stripped remnant core. In cosmic terms, this process is fast. A few 100 million years is a blink of an eye on astronomical timescales. Future civilizations orbiting distant stars may never know this planet existed. We are catching it mid-collapse. HAT-P-67b forces astronomers to rethink how planets form and survive. It almost certainly did not form where it currently orbits. Instead, it likely formed far from its star, where gas giants usually emerge and then migrated inward over time. That journey sealed its fate. Too close, too hot, too inflated. This planet sits at the edge of what can exist. Too light to collapse further, too massive to remain compact, and too close to survive unchanged. It doesn't blur the line between planet and star, because it could never ignite fusion. It never comes close. But it does challenge our definitions of what a planet is allowed to be. HAT-P-67b teaches us something uncomfortable. In the universe, size does not mean strength. Mass does not guarantee stability. And being the biggest does not mean being the most powerful. This planet is enormous, yet fragile. Blazing, yet dissolving. A giant balloon, drifting too close to a cosmic flame. For decades, we imagined planets as static objects, formed once, then frozen in time. HAT-P-67b proves that worlds can be temporary, dynamic, and self-destructive. Planets migrate. Atmospheres escape. Extremes carry consequences. Some worlds grow so large that they begin to unravel. Somewhere in the universe, there exists the biggest planet ever found. Not because it's the heaviest, not because it's the strongest, but because it has been pushed right to the edge of what physics allows. It shines, it swells, and slowly, it disappears. And as astronomers continue to explore the galaxy, one thing is becoming clear. The universe has no obligation to match our expectations, and the biggest surprises are often the most fragile ones of all.